So in this video, we're going to do some work practice problems. So work, remember, is force times distance. Your work units and metrics are joules and foot-pounds if you're in the US measurements. The force units would be newtons if we're in metric and pounds if we're in US. Knowing those is important because it's not going to come out and tell you that it's a force. You've got to recognize by the units. So first thing we're going to do is we're going to look at two spring problems. They're common work problems, and they're the easiest of the work problems. So we've got 7 newtons causes a spring to compress 4 meters from its natural length. Find the work done in stretching the spring 10 meters beyond its natural length. So with spring questions, our force equation, which you saw in the video, is F equals Kx. So in any spring question, your first task is to find the K value. Well, you find the K value because they will always tell you a certain force that either stretches or compresses the spring a certain amount. And that's what we have here. 7 newtons caused it to change by 4 meters. And it doesn't matter if that's a compress or a stretch. We just put it in as force. So we've got 7 newtons for our force equals K times 4. So if we divide the 4 over, we get that 7/4 is K. So our force equation then is just F equals 7/4 x. So now in our integral, we do our work, which is the force times the distance. Well, the force is just 7/4 x. Now the distance that you're traveling, if you have some spring, when we first did integrals, we did Riemann sums and we split our area into little rectangles. Well, it's the same thing with the spring. You're going to split it into little tiny distances that you're stretching and then add each of those distances up. So our distance that it's traveling is dx. So the integral finds the force it takes to stretch each little tiny distance, and then the integral adds up all of those work amounts for the entire interval. So the integral values is where people usually make a mistake on spring problems. The integral numbers are always in relation to the natural length. We want to find the work done in stretching a spring 10 meters beyond its natural length. So that means we're starting at the natural length, so 0, and we're going to 10 meters. Let's say they had told us our natural length was 2 meters, and we wanted to stretch it from 5 meters to 10 meters. So if we said the natural length is 2 meters, and we want to go from 5 meters to 10 meters. Then on our integral there, we would go from 3 to 8. If the natural length was 2 meters, 5 meters is 3 away from that, and 10 is 8 away from that. Okay, so all we have to do is do the integral here now. So we'll have x squared multiply out front by a half, so that's 7/8. Going from 0 to 10. 10 squared is 100, times 7 is 700/8. Minus 0. And we can just leave that as 700/8 if we want. We're in metric because we had newtons and meters, so we would have joules for our unit of work. Okay, here's our next one. Now this is in the packet, which I put a PDF of the packet in case you wanted to print it out. We're going to do several problems from the packet, or you can just do it in your notebooks. That's fine too. So we've got another spring question. 3-pound force is going to compress the spring 1 foot shorter than its natural length. How much work is required to stretch it from its natural length to 4 feet beyond the natural length? So what I would like you to do right now is pause the video and see if you can do this question based on what we just did in the last one. And then when you start the video back up, you'll be able to check your answer. So go ahead, pause the video now. Okay, so our force, our pounds was 3. It changed it by 1 foot. So we get K is 3. So our force is just 3x. Our distance for the spring is dx. We started at the natural length and we went 4 feet beyond the natural length, and you end up getting 24. And because we're in US measurements, we would have foot-pounds. All right, so we're going to go, this is on page 1 in the packet if you decided to print it out. If not, you can just follow along here. So we've got a tank that's a cube. It's got 4-foot edges, and it's filled with water. And we want to know how much work it would take to pump all the water out the top of the tank. Well, something that's written on the top of packet page 1, if you didn't print it out, is that they give you the density of water. So our first task is to figure out the force that we're working with. Because we have pounds, we are working with US, and pounds is a force measurement. But we have pounds per feet cubed. So if we have 62.4 pounds per feet cubed, that means we need to multiply that by a feet cubed in order to turn that into a pounds and make it just be a force. A feet cubed is a volume measurement. We are going to multiply by the volume of a slice of water. Whenever we do integrals, we're really slicing it up into small parts. So the volume is a slice that we're looking at, and we're going to draw the picture in a second. The most common mistake here is people will multiply by the volume of the cube. They'll say times 4 cubed. If you are doing that, it is not correct. It shouldn't be that easy. Okay, when we multiply by a volume in these work problems, we're multiplying by the volume of just a slice. Okay, so when we draw our pictures, if you have rectangular prisms, cubes, cones, you usually, rectangular prisms and cubes, you want a corner at the origin. Cubes, you want the point of your cone, or sorry, cones, you want the point at the origin. If you have a sphere or a cylinder, you want the circular part, the center of it, to be at the origin. So here is our cube that we're working with. So something kind of like that. So it is completely filled with water. This is 4 here, and this is 4. Well, we need to find the volume of one slice. So I'm going to draw in a random slice of water there. The first thing, so that slice is a rectangle with a little bit of thickness. So, well, I guess square in this case because it was a cube. So 2 of our dimensions in that slice are 4 and 4. And then the little bit of thickness is either a dy or a dx. Well, our little bit of thickness, we sliced it horizontally, so it should be a dy because we are chopping the y-axis. Now, we always want to slice it horizontally because all of the water in this slice is going to travel the same distance to get out the top of the tank. If you sliced it vertically, then the water in that vertical slice would all be traveling different distances to get to the top. We want them all to travel the same distance to get to the top, so we'll always slice these horizontally. So this right here, this was a feet cubed, so that wipes out this feet cubed. So these multiplied together, that is going to be our force. So far, we're going to have our integral. We'll have 62.4 times 16. I'm going to throw the dy at the end because we usually like to put that at the end. So this is our force. Now we need to do by the distance. So the distance that we need to travel is from here to here because it goes from our slice out the top. Well, what we learned early in the unit comes into play here. That is not attached to the axis. Let's put in a squiggly. Together, those are equal to 4. And we want to take away the squiggly, which is a vertical line attached to the x-axis. That's a y. So we have 4 minus y for our distance that we have to travel. So the 62.4, 16, and dy, that is the force, and then the distance is the 4 minus y. On the integral, we need to put the places the slices could have occurred. The lowest the slice could have occurred is 0. The highest the slice could have occurred is 4. Now we can pull the constants out front. If we do the 62.4 times the 16, that's going to give us 998.4. We're going from 0 to 4. All we're left with is 4 minus y dy. So what I'd like you to do is I'd like you to pause the video right now and do this integral and then restart it to see what the answer is. So go ahead and pause it now. Okay, so do your antiderivative, sub in your 4 and 0. That just gives you 8 in there. And 8 times the 998.4 gives us 7,987.2. We were in US measurements, which is why we had foot-pounds. So part B is, what if it was only half filled with water? How much work would it take to pump all the water out of the top of the tank? So let's think about what would change. We're still starting with water, so we still have 62.4 pounds. Each slice is still a square with a little thickness, so it's still 4 times 4 dy. So that's all the same. No matter where your slice is, it's still got to travel to the top, so it's still 4 minus y to get to the top. The only thing that's changing is where the slices could occur. If it's only half filled, these slices could only occur at half of the values, not 0 to 4. Now, if you're filling it with water, and it's only half filled, it's the bottom half that's going to be filled. So the only thing that's going to change here is the values on the integral. Now they just go from 0 to 2. And let's see what would change here. Basically, if we go to, let's jump to this step, because it would be the same antiderivative. We'd have 998.4. When we sub the 2 in here, we would have 8 minus 2, and then minus 0 for the others. So that would give us 6. And if we multiplied by 6, we'd get 5990.4. And that's foot-pounds. Well, notice that it's half filled with water, but that's not half of what the work is to move the entire thing. And the reason it is not half is it takes more work to move the bottom half of water out the top than to move the top half of the water out of the top, because remember, work is force times distance. That top chunk of water is moving a shorter distance to the top than the bottom half is, so it creates more work to move the bottom half than the top half, and that's why it's not exactly half for the two of them.